So, go ahead.
Okay. So I don't need a microphone, right?
I think everything is.
Okay, well, I'm very enthusiastic and sympathetic about the topic of this workshop. I remember when I first went to Jilla, that's 1994. It was not long after this NRC report that you were referring to, and of course, Jilla was one of the centres as well as Rochester and some other places. And I think it had, it was a time when AMO theory was sort of undergoing a huge renaissance. I think really changing what people were interested in and moving much more into the quantum control and what we now think of as quantum 2.0 and things like this. I think it was a super interesting time and had a big effect. And I really like the idea of this workshop. I think it's time to sort of revisit this and to think a bit more about this. Although I think the landscape has changed so much. I just have an initial slide here. These are some of the points that are in the abstract for this workshop about topics for AMO theory, quantum many-body quantum simulations, QIP, non-equilibrium dynamics, ultra-fast, of course, and precision measurement and sensing. And you could probably add to this list, but I think one of the things that I notice over time is that really the field has diversified enormously, and it's built bridges with many, many other different fields. Here are some sort of points that I would mention. I think it's almost unlike any other field that it has so many teeth to the comb. There are so many pieces associated with its connections with other areas. Information science is, I think of as a mathematical subject, but it has a huge component in AMO theory these days. Theoretical computer science and complexity theory. We can talk with these people. We have common language now, condensed matter. Space science, I'm going to show you a little bit about one topic that we're interested in that connects with space science. But I would say ever since, I was working with people like Arthur Eckert and so on, way back when I was doing my PhD in Oxford, and we're talking about crazy algorithms and so on for manipulating quantum information, that it's really hard to imagine at that time where this kind of field would lead. But I would say that AMO theory and quantum optics and these other things have had huge impacts in developing the ideas of quantum 2.0. The ideas that not just studying quantum matter, but actually being able to actually control and manipulate it and use it for technologies. This is really what started this NRC review. And I think it's still true that AMO theory is really underrepresented in many different major colleges and universities throughout the country. I think we have sometimes getting students to get permanent faculty positions in certain places and things like this. That was true 30 years ago, and I think it's changed, but it's not changed completely. I think the topic still exists. And I would say this field has developed a lot of extremely important theoretical techniques, and particularly dealing with open quantum systems and measurement, and dealing with quantum noise in general, stochastic and Monte Carlo methods, and in dealing with a whole range of not statistical mechanics, but sort of the time version of that, if you like, non-equilibrium, temporal phenomena, and so on. And then the other thing I would say about AMO theory is that it's quite different to many other areas in physics, and that there's this enormously tight feedback loop with experiments. And you can even have situations where, the feedback loop is happening day by day by day. There are people working on the same problems who are theorists and experimentalists. And it's not the case where you have to sort of generate a substrate, and then you have to prepare the substrate, and then you go and you make your measurements. And then, there are many examples where that tight feedback loop doesn't exist. So I don't know if anybody has any comments, but I think this is an open discussion. These are some of the things I would think of, and I guess over the next couple of days, there'll be a lot more thoughts about this kind of thing. Okay, what I thought I would do though is I would show you, we have a number of things that are going on in my group in Jilla. We're working on things like superradiant systems. We're working on a range of things to do with SUN systems and exact solutions. And we're also working a lot on atom interferometry and optical lattices. And I'm going to talk a little bit about that last topic, just in the interest of time. But I think it's just an interesting focus subject that you know, that I think where AMO theory and experiment have sort of become entwined with some sort of effect. So I'm part of a NASA QPI, Quantum Pathways Institute, and we are building, we're using machine learning basically to control atoms and optical lattices. This is us up here, and I'll show you a little bit about what we're doing in that regard. But it's a sort of a national institute that connects with UC Santa Barbara and also with various places, in particular Texas and Caltech. We're working on the cold atom physics. So this is where the AMO lies. And UC Santa Barbara, in particular Dan Blumenthal's group, are working on sort of developing lasers and integrated photonics. And this side of the diagram is to do with the Texas Space Sciences Research Institute and Caltech and NIST are associated with sort of systems engineering for this project. So what is it that we're trying to do? Well, we're trying to build a very, very good atom interferometer that eventually could fly in space, basically to bring sort of a quantum technology towards precision measurement of planet Earth. So it's quite a big project. There's a lot of institutes involved, and the AMO side, I would say, is the sensor. So this is really where we are trying, this is really a crux of this whole project, is to try to use quantum gases and quantum matter to improve upon classical sensors. So let me just show you what's motivating all this. NASA are interested in measuring gravity, and in particular in measuring gravity gradients, and they're very good at it. For those of you who don't know, there's two major gravity gradiometer systems, GRACE, which has been going through several generations. This is a kind of pair of satellites that fly around the Earth. I'll show you a picture of that in a minute. And GOCHI, which ran for a certain amount of time as the sort of European Space Agency contribution. They measure the gravitational field by flying around the Earth. And this is just a picture of the gravity map. This is the gravity normally in something called milligauss. Milligauss is 10 to the minus 6 G. So it's a CGS unit. And what you can get from that is like information about the planet. So, given that we're here in ITAMP, this is actually quite relevant, I think. This is connections that AMO builds to space science. The gravity field is 9.8 meters per second, sort of on average, if you like, but it varies a lot because the planet is not a sphere. And so you can see this in this map. There are, of course, a lot of other structures on here, and I'm not going to go through any of this, but I'm just going to say that that it's interesting for remote sensing to be able to make these kinds of precision measurements. This is a picture of GRACE. You can see the two satellites here with laser ranging. This is a classical system, and GOCHI is a system that involves different kinds of inertial sensing on classical inertial sensors. So what they're really interested in, and they're kind of amazing at doing this, and our project is to try to bring quantum to this domain. But even with these kinds of classical sensors, you can measure time variations of the Earth's gravity field, and really you want to get down into this sort of nano-G region to be useful, to be interesting. And actually, this is an amazing picture because as you go through here as a function of time, you can actually see all sorts of changes in the gravitational field that are due to things like weather patterns. Anomalies on the Earth, tides and things like this. And that allows geophysicists and atmospheric scientists and so on to build models. And so, okay, so that's the motivation for what we do. And as I said, we bring sort of machine learning, and I think that's one of the interesting parts of the future of AMO, which I would like to point out, that that kind of use of quantum design with the aid of reinforcement learning and other kinds of machine learning is a really very powerful future. So what we do is we try to develop, we try to use optical lattices to build atom interferometers. And this is just to motivate a little bit about why we went down this path. This is just a picture of the F1 cesium fountain clock. And as you know, that going from sort of the microwave domain, which is, if you like, the national time standard, into the realm of optical transitions and of lattice clocks, allowed the precision of clocks to be improved by orders and orders of magnitude. So this is just a picture of a strontium lattice clock, and this is the Allen deviation as a function of time. So this is where the microwave transition sits. Single aluminum ion, which is a 2-electron system, moves into the optical domain. And then as you get lots and lots of atoms in an optical lattice, you get down here by orders and orders of magnitude with a sort of statistical averaging, and it really pushes you into this. It's really the best measurements we can make. So the idea is that optical lattices can provide a really pristine environment for measuring time. And I think our motivation is really to ask the question whether or not that can be extended to measure space, in the sense of position instead of time means for us inertial sensing. We want to measure things like forces, accelerations, gravity gradients, and things like that, basically in complement to what is being done in the optical lattice clocks. So we want to put atoms in an optical lattice. We want to hold them in a pristine environment and try to use that to measure with extreme precision, the small forces on those atoms. And this is obviously a topic that has a long history. I would say it even maybe founded quantum a long time ago. The idea of matter wave physics, this is really underpinning quantum mechanics itself. But ever since the 1990s, there's been really tremendous advantages in just traditional atom interferometry. Basically what you do is you put an atom beam, you have a pulse of light, it splits it into each atom into a superposition of taking 2 paths. A second pulse of light of twice the duration mirrors them, and then you can recombine them with the same pulse as you started with and create 2 output channels which tell you about the differential phase that's accumulated along these 2 paths. So that's a traditional light pulse atom interferometer. And even in the 1990s, people were measuring extremely impressive uncertainties in gravity. It's even right at the very beginning, the use of matter wave physics to measure gravitational fields was impressive. But that kind of system offers certain challenges. It's not very flexible in the sense that once you build a device like this, it's useful for one singular purpose, and it's difficult to go a long way beyond what was even initially demonstrated. There are all sorts of systematic effects and other challenges, and so being able to do this in an optical lattice is really kind of opens up a whole lot of new possibilities. So what I mean by this, so here is an optical interferometer. You've got here the 2 different optical paths. They come back and they recombine. The light pulse interferometer that I showed you, or Bragg interferometer, basically does the same thing, but it does it with the replacement of the light with the matter waves. And so the mirrors get replaced, the matter mirrors get replaced by optical pulses, and the photons going down the paths get replaced by matter waves. In an optical lattice, you really want to be able to build something which is analogous to this device, but replaces these kinds of beam splitters and mirrors and so on with something else. And that something else is actually not very obvious what to do. If you create a Bose-Einstein condensate in a 3-dimensional optical lattice, it's really not very obvious how you can split the atoms and how you can send them along different paths and mirror them and bring them back together. You can think of protocols. They're challenging to implement if you do it with sort of intuition and by hand. And I think that's where I want to emphasize that you can use elements of machine learning to solve this kind of problem, and it solves it impressively and effectively in ways that I think very, very difficult for, just the AMO theorists sitting down with their pen and paper solving equations to come up with. Okay, so I'll show you some of these solutions now. We do this in a variety of ways, but this is the basic idea. There's a learning cycle where we undergo a loop where we have an agent. And the agent is really, you can think of just as a computer program. And the computer program cooks up possible moves to make. And those moves are called actions. And those actions are carried out by something called the environment. And the environment is typically an experiment or as a simulation of an experiment. And then you can evaluate whether or not what you did to the environment was what you wanted by making an observation. And based on your observation, you can cook up a reward and tell the agent whether or not their move was good. And this process is called reinforcement learning, which is used in a variety of, this is really a computer science slide. People in CS do this sort of thing all the time. In fact, I would say it's a CS topic. And you can use it for controlling robots, and you can use it for playing games like chess and Go and things like that. So these elements of this feedback loop, which is this agent, which is typically implemented in some kind of algorithmic way. We use a deep learning neural net, different ways of doing that. And the environment, which is sort of like a simulation of the Schrodinger equation or an actual experiment, can be both. This kind of loop is really powerful for generating algorithms that lead quantum systems to perform certain tasks. So really the goal in this kind of learning cycle is to come up with a strategy that maximizes your long-term rewards. And for us, that could be taking a quantum system from an initial state, which is pristine, to a final state, which is some sort of target. So we do this, we can build these mirrors and beam splitters and other devices that I talked about, which I said are not intuitively obvious how to do, but you can use this kind of learning cycle just to frame the problem in terms of reinforcement learning and ask the computer to solve it for you. And that's what we do. So this is a kind of thing here. Here's our neural network. Here's our actions. Our actions might be the position of our optical lattice, or they could be the intensity of the lattice, or various other properties of the optical lattice. We carry out the actions by solving the Schrodinger equation, and then we look at the observation. Typically, we're looking at momentum of the final momentum of atoms and asking whether or not they produce the solution we want. This is a kind of a beam splitter. You see what we would like to target is atoms going left and atoms going right in a superposition. And so you can simply start off with, the ground block state of a three-dimensional optical lattice and ask it to form that target. But you can also do this, by the way, not only with machine learning, but also with standard quantum optimal control methods. They also can be used to sort of manipulate quantum states and to generate targets. And this is a cycle, an analogous cycle in this kind of QOC field, which is another field, I would argue, maybe engineering. They use them to control things like motorbike stability and planes and things like that. You basically, for the quantum case, what you have is a very similar sort of cycle where you start off, you apply a control, the control evolves according to some Schrodinger equation. Typically, when you optimize this to try to achieve your target, you'll end up with moving the solution away from any solution of the Schrodinger equation. So you sort of take a gradient descent in terms of your control field, and then you project back onto solutions of the Schrodinger equation, and you go around with a gradient descent method, and you end up in some local minimum. So these things are standard methods as well, and they both work. And what I'm showing you here is the position of an optical lattice as a function of time from these two different solutions, and there are gazillions of possible beam splitters in 3D optical lattices, which I don't think is something that I would have guessed. You can just shake a lattice around, and there are lots of solutions for making beam splitters doing that. Every time we would run this, we would initialize the neural net differently, and we would end up with a different solution. So, and we tried these things in the lab, and they all work. So it's kind of surprising. Okay, so in the lab, what we do is, I'll keep on time here. So we make BECs. This is kind of a standard set of slides here, if you like. We start off with a magneto-optic trap. We cool them down using subdoppler methods, PGC, compressed mark. Yeah.
You said you had these zillions of local minima.
Yeah.
Presumably they're not all perfect. They're local minima. How good of a beam splitter are you getting for all of these?
Yeah, so I think it's harder to get more than about 99% fidelity. I don't actually really know the answer to that. I think with more computing power and more intelligent people, we could come up with better classes of actions and we end up with better solutions. I think there's a lot of open questions. So we load these laser cooled atoms into a cross dipole trap. This is all optical evaporation. You can see it cooling down here. And then in this, as it cools down and we evaporate the hottest atoms, we end up with sort of the classic three pictures. So we make a BEC in an optical lattice. It contains a lot of atoms, maybe 200,000 rubidium condensed atoms. And it does it in a way which is all optical. So there's no spin degree of freedom in here, although that would be a subject which would be interesting to think about in the future. And we've been working hard on this experiment. This is actually only from August last year, where the table was basically empty. And then 7 days later, we had BEC here. So I would blame Katie for this. It's her up there. You have to have little people in this experiment because they have to take their data from above. So anyway, this is kind of some world record in terms of making BEC, I would say, from scratch in 7 days, but that's another topic. But it's a very confined experiment. It's only fits on the end of a table. It's only about would probably fit in a cubic meter box. So it's not a deployable thing that we could yet put in space, but it's sort of moving in that direction. This is a very hard experiment because it does a 3D optical lattice and there's no retroreflection of beams. So every lattice beam has to be individually sent into the system and controlled so that we can move the lattice around. Anyway, in the crux is that we have 6 beams going through a single point here, and you can see the lattice is made by 2 Cartesian orthogonal directions here, and a vertical one which is actually reflected off a little mirror inside. And that allows us to create a vertical lattice, and so we can make a 3D crystal. So you should think about this as something, like this, where the atoms are sitting in little points. We can make this lattice have different kinds of topologies, and every one of these laser beams is controlled by an acousto-optic modulator, which allows us to move the lattice as we want in space. And so I think there's a lot of condensed matter Hamiltonians that can be replicated in this kind of system. So it's actually very flexible. I mean, it's not just something that can be used for atom interferometry. The system is basically, in terms of theory, block states. So if you've got one lattice made by 2 counter-propagating lasers here, you've got a Hamiltonian, which has got kinetic energy and potential energy. This is the periodicity of the lattice. And 5t is the position of the nodes and antinodes. And that's the thing that we can control as a function of time. So the eigenstates of the system then are the block bands with different quasi-momentum, and there's some Brouwer zone here. And so we can manipulate the quantum wave function amongst these different kinds of states to do the things that we want. Now, in fact, there are 2 classes of block bands here that are important for us. This is the low momentum contribution for 0, 1, 2, 3, and 4, the lowest few bands of the lattice. These ones here, 0, 1, and 2, are below the depth of the potential wells. So that means that they're fixed in space and can't move. These are, if you like, valence band states in a solid state material. They can't propagate through the system. The lowest state is basically 0 momentum, but has a bit of other things in it. And all these 3 are sort of locked. Once you get above the depth of the lattice, though, you get into the conduction band. And these are basically parabolic, and they can move. So this is the idea of building interferometers, because this 3rd state and 4th state up here are basically made up of propagating -4 and +4 h bar k equal superpositions. And so you can think about going from here to here and creating a beam splitter where you take a condensate and you split it into 2 possible paths. So what we actually see then is we drop this and we have a look at the momentum distributions in the final thing. So if we see something like this, we know that we've got the condensate. We can do that in 1D, 2D, and 3D. So we have like 3 dimensions going on here. And we have cameras on all these different axes so we can see this thing. You see these kind of diffraction patterns, these far field images of the momentum distribution when you drop the atoms. In 1D, you see this. In 2D, you then see the peaks going in all the different dimensions. And in 3D, you can look from all the different directions and see basically a diffraction crystal. And so that's the observable that you'll see in this kind of thing. And these are just images from the experiment. You can also like ramp up the lattice depth, by the way. And so this is sort of the Greiner block Esslinger superfluid mild insulated transition. So it's actually important that you have like coherence between the atoms across all 3 dimensions in order to see this diffraction pattern. And there's a certain quantum phase transition point here where it goes over into the insulating phase. So that's actually another interesting topic because a lot of things happen around that point. And I'm going to just show you now that this kind of works. So we have here a given phase as a function of time. So think about this as a very, very strange way of moving the lattice around, moving it left, moving it right, and with some funny frequencies in it. You know, you're probably not going to sit there with a pen and paper and cook up a profile like this, right? But the computer will spit this out in just a few minutes, okay? So it's surprising. Like if I showed you this, you probably would say, no, that's never going to work, right? If I apply that to a lattice, I'm just going to heat the atoms up. Well, this is what it does. This first part here is a beam splitter. Here's a condensate. It produces after this time here, atoms going left and right with 4 plus or minus 4 h bar k in momentum. This thing here is a mirror. It switches that one to this one and that one to this one. And we can see that, by the way, by sending them all one way. And then this one here is the reverse of this, which is a recombiner. And you can see after this ridiculously complicated signal shaking, we end up with basically the condensate back with really high fidelity. We can actually do it in 2 dimensions at once as well. So we can split the atoms into a superposition of going out in a square pattern. They go out in all directions, like a 2D interferometer. And then they come back from their 4 different directions and recombine. And we see him basically the condensate. So you've got something like an interferometer, but instead of like the 2 ports that I showed you with the light pulses, here you have like 49 ports. Okay, and then the problem becomes like reconstruction of the signal from a 49 output sensor. Okay, and that's an interesting topic in its own right. Yeah.
Jonathan, so here everything is in momentum, right?
Yeah.
Do you have also a representation coordinate to get an idea of how condensed, concentrated
Yes,
the thing
exactly.
remains?
I'm not showing those here just for the sake of time, but we can actually see the atoms doing this. You know, they split by a lot, and it's easy for us to in situ image them and actually see the interferometer as a function of time.
And requiring like a localization of the way packet imposes additional constraints of the thing, or
Right, so
something that you don't need to do.
well, you can see here from the far field. So we turn the lattice off and drop them, and then we look at the diffraction pattern. So from the width of these peaks, you can get some idea of what the coherence of the condensate is, and it's going over many, many tens of lattice sites, you know, and you can see that by how sharp these fringes are. I mean, the quality of this data is really awesome, actually. You know, like I don't know if you've seen, but this is, you know, this is pretty. The images are very clear. Let's just say, okay.
So maybe I have a.
Yeah. Okay.
Is there a way that you can also correct for these missing lattice points in this last image of 2D, like here?
Like here.
There's some missing.
Yeah. So I think there are a lot of technical improvements that can be made here. Okay, like that's another subject. There are. I think it's early days for this. Okay, like there are things like mean field effects, collisional effects. There are things like how exactly you want to do the interferometry. Whether these, like as Caden was saying, like whether how far we've got along the actual machine learning here. So I don't know. I would just say that this works and works well, but I think there is potential to do a lot better. So this is I don't want to take too long here, but this is a picture of the interferometer in space. So you should think about this. The atoms are going from the valence band into the conduction band, and they're propagating through the lattice sites, and then they're being mirrored and coming back, and then being put back into the valence band, and then we can look at them by time of flight expansion. So it's some sort of picture that looks like this, and that can happen in 1D like this with a propagation delay. So we can send them as far as we want and then bring them back. And we can also do that in 2D with the same sort of picture. I can't really show you a 3D lattice here, but you can imagine filling in all this with an optical lattice, and they go out in a square pattern and come back. So one of the questions that you might imagine here is, well, this is a new kind of sensor in a way, because we can measure a vector acceleration here, which is what I said initially with the light pulse interferometers, is you're kind of hardwired into whatever configuration you build into your apparatus. But here, because we're sort of doing it by moving the lattice around, we can program the lattice to perform different functions. And this is an example of a vector accelerometer where we're using that square pattern that I just showed you for 2D and accelerating the lattice with 2 dimensions at once. So both dimensions the same, but scanning from minus 0.2G to plus 0.2G. And what you can see here is in the output diffraction pattern, there's a kind of fingerprint. And from that fingerprint, you can deduce what the value is of the acceleration. So this is maybe a clearer way of representing it. As we change the accelerations in 2 different dimensions and look at the 2-dimensional diffraction pattern, all these different fingerprints can be mapped to a given value of the parameters. So this could actually be a real sensor that could actually have use. People really want to be able to measure multiple parameters at once. So what we can do then is we can take these fingerprints and we can just sum them up along the X or Z axes. So these two different axes here. And what you see here is that as a function of the acceleration, you've got sort of fringes, but it's multi-port fringes, not like a normal interferometer. Nevertheless, if I give you an image like this, you can take a sum on the X and the Z direction and look up here and find out exactly what line that fits to in a sort of mean square error sense, and use that to reconstruct the acceleration that was applied to the instrument. Yeah.
Sorry, is each of those dots coming from an independent experiment, or are you
These dots or
on the right?
these dots? So each one of, so we did 41 scans across here, and we did multiple runs of each one of those scans, and that's what the error bars are. So you get a mean value and an uncertainty. And you can see that it's really very high contrast in here, right? So you can now, if I give you one of these images, you can look up over here and say, yes, it was this acceleration. Yeah.
I'm kind of curious, there's kind of an implicit commentary here about the effective inertial mass of the atoms, the lattice. Do you want to comment on how that impacts the accuracy of this technique?
So by inertial mass, do you mean?
Oh, when I mean the lattice, the atomic momentum relationship, right? K to velocity, that relationship is not quite fair mass.
Exactly right. So
that's
but on the other hand,
calibration problem.
yeah. So you will see the effective mass change as you use different block states. But once you go up into the conduction band, it becomes extremely close to parabola. In fact, the 3 and 4 states, for this is a 10 recoil deep lattice, the 3 and 4 states are just in the conduction band, and the splitting is absolutely minute. Like, so that splitting tells you something about the difference between the even and odd parity solutions of the lattice, and they're almost free particles. So these things really do expand with 4 h bar k, which is the momentum that they get by absorbing.
Okay. And what is the accuracy constraint this produces?
The accuracy
constraint that this produces. So this limits your accuracy. What is the value?
Actually, what it does is it introduces gap protection. I don't know, maybe we can talk about this later, because it's actually a really interesting comment, but it's also kind of complicated, But there is a point where if you enclose too much area, the gap protection actually removes the signal that you're interested in. You have to bias away from 0. So it can be dealt with, but
no, stop there. Thank you.
Okay, so anyway, this is just like reconstructing the points against themselves. We'll just quickly show you that you can do this by not only looking at like the amplitude of a two-dimensional vector acceleration, but if you change the direction of the acceleration around the clock here, so keeping the magnitude the same, 0.1 g in this case, but changing the direction, and then looking at the fringes you get, you can take each one of these fingerprints and reconstruct the applied acceleration. So actually it really does measure. This is really a multi-axis accelerometer, which is something that people in this field have been trying to build for a long time.
How sensitive is this to the precise shape of the control? I mean, how robust would this location be?
Yeah, if you change the, so we can do things like low pass filtering the control field and see if it ruins the data. And to some point, as long as you are, not including, so if you can remove frequencies that are much larger than the frequency range that you get from the recoil frequency of the atoms. Beyond that, they don't care because they're massive objects, and below that, they do care. So it's kind of it's very easy to answer that question in a way. But these beam splitters take things like 100 or 200 microseconds, so they are almost instantaneous. Actually, they're so close. Yes.
You probably said that, I didn't forget. So this reconstruction, is that also machine learned?
No, but it could be actually. Like, we don't do that. We bin these up and just add up pixels in each one of these little momentum peaks, which is the most naive thing you can do. But there is information in here that would be interesting to study. So you could use convolutional neural nets.
I would think so, because you have a lot more data than what you can do.
I know, we're very naive, Yeah. We're doing very simple things here, but I totally agree. There could be correlations as well in terms of, you get entanglement of atoms when you generate quasi-particles like this. And so there's a lot more to the story, I think.
And another question, do you have to regularize for your pulses for how fast they change?
What do you mean by that, regularize?
So usually there is a I mean, from our own kind of somewhat naive pulse generation, if we do that, we get pulses that change so fast that the experiment cannot deal with that. So there are basically two ways to deal with that for us. Either we make a regularization term which says that which advantages slower changing pulses, or what we do, we kind of just have a quickest change, make one learning run and put that in as a new starting point, and then take this constraint away and get actually a pretty good solution, because at least in my experience, this really fast changes introduce the biggest errors.
But the bandwidth of our AOMs is really broad compared to the frequency components of our control fields.
Okay.
So we don't need to do that. I understand the point you're making, but we can actually learn off the computer. We can load them onto the waveform generator. We can run the experiment, and we see almost exactly what the computer produces. Like that it's really quite amazing, actually, how it can be done like immediately, and the ability to control these wave functions. I'm surprised at how well it works. So I'll just quickly show you that, one of the questions that you might ask is, how good can a device like this be? Because, can it compete with, the real traditional atom interferometers? This is just a picture of Bayesian reconstruction, just running the experiment many, many times and looking at the posterior probability distribution contract down. And so by looking at multiple runs, you can get an idea of what the ultimate sensitivity is, to which what's the uncertainty in your reconstructed parameters. And so we do that sort of thing. This is just an example of averaging down with 200 experiments. It's a vector accelerometer, so there's two lines on here. This is the uncertainty as a function of shot number, and this is for X and Z directions. And as you average down, statistics should tell you that this should be square root of n. And so you see the square root of n lines, and you can histogram samples from the different experiments like this. This is 3, 15, and 100. And you can see basically that our reconstructed images is following what you would expect for statistics. This is the value, uncertainty, and then the image that you get. So we've been working a lot on this. This, for example, is a range of different accelerations in the X and Z directions. And so you see the different fingerprints, and you see us able to sort of reconstruct what we apply, and then the averaging coming down is the square root of n. So this is sort of just demonstration that it really does work as a sensor. But what we want to do now is really to push this. The ultimate utility of this device is really to do with what uncertainty can be achieved, and that's enabled by expanding the atoms, by increasing the area that's enclosed in space-time by an interferometer like this, which means running it for a long time and having very long coherence lengths. So this here is an example of 5 milliseconds. We're expanding here the atoms by a few hundred microns. They're going out, they're coming back. You can see here the interference fringes that you reconstruct by doing this. This visibility is really quite high. And then we applied this 0.0008 acceleration to the lattice, and then average down, and you can see here that it's starting to become quite interesting, even on that scale of the G of the planet Earth that I showed you right at the beginning. I don't know how far we can go with this. We've split the atoms by many hundreds of lattice sites, which is what happens in a 20 millisecond a scan. And you can see here basically that there is high visibility in what we observe, but really hasn't. This is kind of preliminary data. This hasn't really been studied. But when you do this, you get. I'm sorry about this cut and paste error, but you can see here you really do get into extremely interesting numbers. And so, we don't know how far we can push this technology. We are really working on stabilizing all the noises in the system and kind of seeing how long and how long we can keep the coherence and how far we can average down before we kind of start to hit the technical limits of our experiment. Anyway, I'm going to finish there. I'm just going to say there's a lot of things you can do with this. It's kind of like bringing machine learning and AMO theory into the actual quantum design of these experiments. It's proved to be quite effective. I think we've just scratched the surface. We want to like look at different kinds of species, not just rubidium, but also strontium, as well as the different kinds of devices that we could make in 1D, 2D, 3D. We've already shown here a multi-axis sensor. That's not so easy to make with an atom interferometer. But it's also not the only kind of device that you could build. You can imagine multi-axis gyroscopes and all sorts of other things. The other part of this is connections with classical fish information and quantum fish information. A lot of the machine learning ideas that I have here, they can be applied to quantum information theoretic ideas, and you can make protocols that are insensitive to the noise of your specific experiment. That sort of thing turns, I would say, is a very powerful direction forward in quantum metrology. We want to improve the experiment and a lot of technical things and focus on removing noise. So we're going to be, as part of this Quantum Pathways Institute, we're going to be pushing this technology forward as far as we can towards deployability and towards making real devices that are useful for not just our community, but connect with space science and the other people that are associated with this research project. So with that, I think I'll leave it.
Thank you.
Time for further questions. Audience. Yep.
First of all, thank you so much for such a engaging and deep drive in one area and then the broad perspective for the rest of the workshop as well. It's awesome. One technical question was, is there a relatively straightforward path to go from the mirror pulse that you have right now to a hold pulse?
Yes.
And have you tried it?
Yes. We have actually. If you're interested, I can show you some data on this. What's kind of neat is that you can take atoms, like in a photon interferometer, you can't put a laser onto a 50-50 beam splitter, have it go out, and then hold the photons at the mirrors for like 10 minutes, and then say, okay, now I'm going to flick a switch, and then bring the photons back together. If you could make a wonderful Sagnac interferometer or something like this, right? Can't do that because photons are fragile, but with atoms, you absolutely can do that. You can take a BEC, you can split the atoms, and when they're at their first extents, you can put them back into the valence band. And you can just sit there. And then when you've decided that you've got the sensitivity that you want, you flick a switch and bring them back together in the field. We can do that in the lab too. So it's kind of neat.
And what are the limits to your hold time?
Your ability to maintain the coherence in the valence band. Now it's an open question because there's lots of ways you could do that. It's a quantum design problem. How can I really put things in the ground state in a stable system so that there's no dephasing? You need two different states, obviously. Anyway, it's a good question to ask me because it's really a neat aspect of this that I didn't go into.
Thank you.
Any more questions?
Maybe more of a joke, but if your trajectory is anything to go by, it seems the future of AMO theory is being an experiment, doing experiments, or no, but I do have a real question. Maybe there's an observation you want to comment.
No, that's not the only thing. So not only doing experiments, but we're out of business because machines are going to take over.
Okay, but then a real question, can you just say a little bit more about the actual machine learning methods that you're using?
Yeah, so what we do is, so these are done on workstations. They're not humongous, great big platforms. They could be. We don't even use graphics cards to do this. We could do. They are double deep neural networks. So they have, an input layer and a number of hidden layers and then an output. And the output produces what are called Q values. And they tell you about the possible qualities of making moves. Like in chess, the input would be the position of the board, and then the output would say move the pawn 2 squares here. So for us, the input is some feature of a quantum system. It's typically not the wave function because it contains a huge dimensionality. So you have to decide. So we would pick something like the momentum probability of the cloud. And then the output would be different possible actions you can make. Maybe move to the right by this amount and move to the left by this amount.
Mm. So, but then, so this is like open loop. You're doing all the optimization classically, and then
yeah, we thought we would have to do closed loop on the experiment, but actually the truth is we haven't needed to. So we do open loop learning. We come up with wave forms and we digitize them at 50 nanoseconds, and we load them onto an AWG and we apply them to experiment.
And then the simulations you use in that are just non-interacting condensate, or do you have to do
We've
GPE or
done
something?
both, but these ones here were learnt off a non-interacting VEC.
Okay.
We find that once you get sort of more than 30,000 atoms, the mean field effects become pretty significant. So that's actually going to be a challenge going forward, is dealing with interactions.
Curiosity, maybe it is completely stupid, but I mean, cubic lattice, and there are so many structures that are multi-lattice. Can you use multi-mode laser to shift one to the other?
I really think we've just touched on this. Okay, once I start to get into more complicated lattice structures, you know, and I get direct points, I get the ability to entangle atoms together. I think there's just this, you know, this kind of ability to make a design a quantum system, and then use machine learning to sort of like go from some state to some other state that you're interested in, is sort of opening up a playing field, you know.
So it is not inherently stuck to cubic.
No, but our experiment, I mean, we've got 12 beams going through this cell. Okay, so it's not so easy if, you know, if you come along and say, we want something else, but in principle, yes.
So you split up your kind of sequence into very nice chunks. Is that where you feed the reward to the agents each time, or do you intersperse it through the whole sequence?
So what we've done here is we've used machine learning to design components. So to design a mirror or to design a beam splitter. And then we cascade those components together by just stitching the waveforms together. Right? So you can build an interferometer by beam splitter, mirror splitter, with propagation in between. But you can also do what we call end-to-end design. So you can say, I want to start here with a BEC, and I want to end up here with something that has high classical Fisher information for measuring phase. And the computer comes up with something, and that works really well as well. Okay, so but you end up with something which doesn't look like an interferometer. You've just got like wave function going out and interfering in some complicated way and coming up with a pattern, and that pattern is super sensitive. So I didn't show you anything.
And so in that case, you only put the reward right at the end.
And then you would just look at and the reward would be based on classical Fisher information, which is what you actually measure.
So let me give it a very end with a note question. So given that Dano is in the picture, how soon will this thing go into a box?
So we built this first experiment. The second experiment is sort of a more deployable version of this, but there's no plans in the Institute, which is a 5-year initially funded project, to build an actual flying system. But it's really...
You see within a decade.
Yeah, exactly. I mean, if we are able to establish a proof of principle technology within this first period, the plan is to move then into a field deployable system.
Thank you very much.